Hi. Today we will be discussing the third of the solid principles, which is the Liskov Substitution Principle or LSP. Let's start with the formal and simple definition of the LSP, and then we will see a compliant example for LSP. Then we are going to see obvious violations of this principle with the popular example of rectangle and square classes. Next we will see an attempt to fix the issues between square and rectangle, yet at some point it fails owing to a violation of LSP. Then let's see two more clues to violations of LSP, and then we will come to the most important section of solutions to LSP violations. Finally, we will see how the LSP extends beyond inheritance in the broader aspects of architecture design. We will wrap up with some final remarks about the LSP. One additional note here, we will use the words derivative and subclass interchangeably throughout this discussion to refer to subclasses. Formal definition of LSP, as Barbara Liskov first wrote this principle in 1988, was like this. What is wanted here is something like the following substitution property. If for each object O1 of type S, there is an object O2 of type T, such that for all programs P defined in terms of T, the behavior of P is unchanged when O1 is substituted for O2, then S is a subtype of T. This is highly mathematical, and we will see the simpler version. Subtypes must be substitutable for their base types. Next, in this perfect example of a payroll application, we have an employee base class and two subclasses, salaried employee and hourly employee. For this payroll application, either the salaried employee or hourly employee are perfectly substitutable for the employee class because they share the common methods and common attributes when it comes to inheritance. This is a perfect compliant example for the LSP. Next, we will see a violation of this LSP. When the user considers a rectangle, we can see a square is also defined as a subclass of rectangle. Yes, in mathematical terms, we can say a square is a rectangle because they have four sides. But when we consider it programmatically, there are issues because squares have equal sides, unlike a rectangle where the height and width can vary independently. If we try to see the clues why a square is not perfectly substitutable for a rectangle, we can see that a square cannot call either set height or set width independent of the other, because even though the rectangle can call these independently, a square cannot do that. So there it breaks that substitutability. Then actually a square does not need both width and height attributes. Just one attribute like side length is enough for the square because all four sides are equal length. So in a way, this is memory wasteful. But you might say just one extra attribute cannot harm a lot. Yes, that is true. But let's assume something like a CAD application where everything is derived or displayed as rectangles and squares. If you let an additional single attribute for the so many squares that it will create, this will have so much extra memory wastage. So those are certain clues that direct us and indicate us that a square is not perfectly substitutable for a rectangle. However, we can attempt to fix this independence of set width and set height using this approach. Here I have defined a rectangle class and a square class as a subclass of rectangle. So how we are fixing that issue is, whenever we call set width, we call both set width and set height of the rectangle class. So both those values will change at the same time. Similarly, for the set height operation of the square class, we are calling both the set height and set width from the rectangle class. So that way we can make sure that whenever we change one attribute, either width or height, the other attribute also changes. However, there is another issue here. We can see we have a checkArea test method that takes a rectangle object and sets the width and height and then assumes and asserts whether the area is 50. If we pass a square object to this, what would happen? It will update the width or the side to 5 in the first line and set the side to 10 in the second line. And the area would be 10 times 10, which is 100. So if we pass a square object, this assertion would fail. There is an option for us to use an if condition in the checkArea method to check the type of rectangle to make sure if it is actually a rectangle or square. But that again violates our second solid principle, open-close principle, which says modules should be open for extension but closed for modification. If we use if conditions every time when we introduce a subclass, we would need to modify the base class. So a violation of LSP becomes a latent violation of OCP2. Another important conclusion here is that a model viewed in isolation cannot be meaningfully validated. The validity of a model can only be expressed in terms of its clients. So if we consider rectangle and square in isolation, you can say they are self-consistent. But when we try to see through the eyes of external users how they presume the behavior of these classes, we can see there are inconsistencies. So that is an important validation we need to keep in mind. So if we discuss about this violation, we can think about a discussion going in this direction. Somebody would say this checkArea function, whoever wrote that, is at fault. Another person could argue that checkArea had every right to assert this invariant that width and height are independent or they are not the same in a rectangle. So he could argue that the author of the square has violated the invariant. However, when we look at the square, we cannot say that the author of the square did violate the invariant. It was the decision to derive square from the rectangle that violate the invariant of the rectangle that is causing all these issues down the line. So as good architects, the decision to derive from a particular base class is a very important decision we need to make, considering all possibilities to the foreseeable future. Next, there are two other clues that direct us to find violations with regard to LSP. Degenerate functions in derivatives. The f function in base is implemented. However, in derived, it is degenerate. Presumably, the author of derived found out that function f had no useful purpose in a derived. Unfortunately, the users of base don't know that they shouldn't call f, so there is a substitution violation. The presence of degenerate function in derivatives is not always indicative of an LSP violation, but it's worth looking at them when they occur. Next clue is throwing exceptions from derivatives whose bases don't throw them. If the users of the base classes don't expect exceptions, then adding them to the methods of derivatives is not substitutable. Either the expectations of the users must be altered or the derived classes should not throw the exceptions. Next, let's consider what are the solutions to the violations of LSP. The first solution is factoring. This means identifying and extracting common methods and attributes into a base class, then deriving the subclasses from that base. This ensures the subclasses are truly substitutable. Factoring is a design tool that is best applied before there is much code written. So as you can see here, we have been able to factor out the three common methods in both rectangle and square, like this get top left, get bottom right, get area methods from rectangle and square, and use them in this quadrilateral base class, and then we will be extending rectangle and square from this base class. Certainly, if there were dozens of clients of the rectangle and square class shown, we would not have had an easy time of factoring out the quadrilateral class. When factoring is possible, however, it is a powerful tool. If qualities can be factored out of the two subclasses, there is the distinct possibility that other classes will show up later that need those qualities too. Next, there is a more robust solution that we can implement in an architecture at any maturity level, which was suggested by Bertrand Meyer as design by contract. What is meant by design by contract is specifying clear pre and post conditions for each method in the base class and ensuring that derived classes adhere to this. So what this means is whenever you specify a class, you specify a contract that determines how the methods or the functions in that base class works. If any of the classes wish to derive from this base class in the future, they will need to comply with the pre and post conditions of these methods. So before it starts the execution of the methods, it makes sure that the preconditions are true and then executes the method, and after the method execution, it checks whether the post conditions are true. There is a rule that Bertrand Meyer defined for preconditions and post conditions of derivatives or subclasses. It says that a routine redeclaration in a derivative or subclass may only replace the original precondition by one equal or weaker and the original post condition by one equal or stronger. In other words, when using an object through its base class interface, the user knows only the preconditions and post conditions of the base class. Thus, derived objects must not expect such users to obey preconditions that are stronger than those required by the base class. That is, they must accept anything that the base class could accept. Also, derived classes must conform to all the post conditions of the base. That is, their behaviors and outputs must not violate any of the constraints established for the base class. Users of the base class must not be confused by the output of the derived class. Let's try this with the square and rectangle example that we discussed earlier. In this example of rectangles set with method, it had a post conditions with two invariants. It said after the method set width is executed, its width should be the new width and its height should be its old height. But if you see the post conditions of square, we are dropping the height invariant and we are asserting only the width equal to the new width. So we are dropping a part of its post conditions. So we are actually making the invariant weaker in the derivative class. Hence, this is a violation of the design by contract, and that is why we are failing to comply with the LSP. Let's see the same in a diagram. Here you can see in the subclass contract we are dropping a part of the post condition out of the two invariants that were present in the base class. We are dropping one invariant when we create the contract for the subclass, which is not acceptable in terms of design by contract post condition rules. So where should we specify these contracts? So the ideal place to specify contract is in unit tests. What happens when they are specified in unit tests is that they clarify the behavior of that class. They clarify the behavior of that particular method. So whoever that want to derive any methods, any classes from the base class, they can read through the unit test and identify and reasonably assume about the class that they will be deriving from or they will be using. So that is the importance of specifying contracts in unit tests. Finally, we will see how the LSP extends beyond inheritance. It is not applicable only for the inheritance aspect, but if you are thinking of a much broader perspective of architecture, you can implement the same for API design as well. Let's assume we are creating an aggregator service for all delivery services such as DoorDash and Uber Eats. If you create a put call to ubereats.com, let's assume this is how you will be sending your request. And in contrast, for the DoorDash, you have a similar URL for the put request. But instead of the order, it needs to specify an order number. This is the clash, and this is a conflict between the two APIs. If you try to create a unified service, unified API to support both these endpoints, you will have to violate the LSP because both these APIs are not substitutable for each other. However, as practical developers, we ultimately need to trade off between 100% compliance for LSP, which makes code unnecessarily complex, versus just good enough for the work. This wraps up our discussion for Liskov Substitution Principle. If you like this content, please like, share and subscribe for more of the similar content. Hope to see you in another video. Until then, happy coding.